Josh came from the physics background and got his undergraduate at Reed College. Actually, that's where Steve Jobs went to college, but he didn't got a degree. But Josh got, yeah. And then Josh got his PhD at Queen's University, Belfast. And he has been working in the field. It's a combination of material science, earth science, actually. And so he has been focusing on various tomography techniques, and including the one that is going to show to us that not only the analysis that physical and chemical analysis will do, but also combines with machine learning in his research. So uncovering structure in a cloudy zone, a data-driven microscopy challenge. So with that, Josh, please.
Thank you for the wonderful introduction. Yeah, so today's talk, before we get going too far, I'm just going to acknowledge the work that I'm talking about today was conducted when I was still based in the Department of Earth Sciences and the Department of Material Science in Cambridge, working under Richard Harrison and Paul Midgley. A lot of co-authors on the work that we did today would have been Robert Blucas, Sean Collins, Ben Martineau, Alex Egeman, and Zanib, as well as working with collaborators in Oxford in the Department of Materials, Paul Baggett, who did the atom probe work. And this was all funded under European Research Council grant, nanopaleomagnetism. So to get into this, this is going to be kind of the materials, or a planetary materials process history challenge. So you could think of this as starting from a chondrite, and even though today's talk is going to be focused on iron nickel meteorites, the same basic challenge happens, which is that we understand that planetary materials form in the early solar system as chondrules. And again, because I come out of a rock magnetism, paleomagnetism group, we're very concerned about how do these chondrules record magnetic fields from the early solar system that maybe acquire a remnants. They then accrete into a larger meteorite that might then get embedded into a larger body. And might get erupted and eventually find its way back to Earth. And so throughout all these steps, we've had a very elaborate materials processing changes where materials have undergone changes, mineral transformations, shocks, deformations. All of these leave their traces in one way or another on the sample. And we need to try and backtrack from these very small samples back to the physical processes that led to building them and how we understand planetary evolution in the early solar system. So another way to think about what we want to do is we want to take something that's a geophysical measurement, which is something that's usually large in bulk. And so in paleomag, that means taking a 2.3 centimeter core like this and doing a magnetic demagnetization of it, this Zegerfeld plot, for example, whereby how we thermally demagnetize the sample, we can then hopefully understand the direction and magnitude of prior magnetic fields. However, as I showed here, this is a fairly large macro scale sample, and this has limits on what we can look at. So in a paleomagnetism sense, there's been a new approach, which is now what's called the single crystal approach, which leverages the fact that we now have very advanced magnetometers that now push our spatial resolution by either using nitrogen vacancies in the quantum diamond magnetometer or scanning squid magnetometers down to about the single micron scale. However, even with this advanced single crystal approach to paleomagnetism, we're still averaging over thousands of magnetic signal carriers because a good paleomagnetic recorder is on the order of 100 to 200 nanometers in scale. So if we want a 200 nanometer recorder, but we only have 3 microns of spatial resolution, like all other geophysical and some geochemical measurements, we're left with the question of what am I actually measuring? So to address that, we're going to examine how I address this on planetary bodies. And in the case here, in particular, looking at some results from some pallasites and some iron nickel meteorites. And we're going to start talking about this deconvolution texture called the cloudy zone. So to give you a flavor, though, before we do that, let's talk about what I mean when I take a microanalysis measurement. So most of the measurements today are going to be done in a scanning / transmission electron microscope. So I can either run it as a scanning transmission electron microscope or just in pure transmission mode. Regardless, the data we're going to look at resolves on two different ways of interacting with the sample. We shoot high energy electrons at the sample. These interact with the sample and they can emit characteristic X-rays in a spectroscopic technique known as energy dispersive spectroscopy. We'll talk more about the results of this, but these are characteristic of the material you're looking at. So different atoms give off different X-rays. And by looking at relative proportions of those X-rays, we can make quantitative estimates of what's in the sample. Similarly, when the electrons pass through a very thin sample, they can diffract, which means that if we place a detector on the diffraction plane, we can record diffraction patterns. And this second one is the second bit of the crystallography that we will hopefully look at. So I have a way within a STEM instrument to look at both chemistry and crystallography. And we're going to use this to our advantage to understanding some very early complex materials. So one way to understand this and what I'm doing here is we're going to look at these iron chromite needles found in the olivine grains from the Admire palisite. The question that I was presented with by my collaborator Claire Nichols in this case was, are these needles magnetic? And whether or not they're magnetic comes down to what is the ratio of iron to chromium. And this is a very difficult measurement. Traditionally for electron microprobe or standard EDS in an SEM, because what ends up happening is due to the interaction volume, the signal for the needle gets convoluted with the signal from the olivine. And so figuring out that exact ratio is very difficult. So the solution we present and the way that we're going to proceed with a lot of the rest of the analysis in this talk is we take it as a statistics problem. As opposed to just thinking about I have two phases, I instead think of that I have a little over 11,000 by 700 pixels in each direction, which means that really I'm looking at just under 900,000 spectra. So this now, which each spectra has 2048 energy channels on it. So this now is a high dimensional data set. So if we use dimensional reduction techniques such as principal component analysis or non-negative matrix factorization, we can now unmix these overlapping signals. So what does this have the result in this sample? So the first thing is again, this is your standard equation describing how deconvolution works. This is a slide mainly meant for the more physicists in the audience because they need equations. And the key bit here is that the spectroscopic data, any one spectra, is thought of as a linear combination of both a loading weight and a linear factor. And this factor here is some spectral shape. And if we deconvolve it such that we also apply a non-negativity constraint, this gives us non-negative matrix factorization. And what we're able to do then is first examine that we can see that two factors are needed to explain about 87% of the data. And everything above this is uncorrelated noise. And this is very true because in the case of this map, it's a low count spectra. So we're trying to work very fast as well. And when we make that condition, though, we're able to get these two factors look like both the chromite and, the chromite here in factor 2 and the olivine in factor 1. And the different intensities, especially on the thinner needles on the right-hand side of the screen, we can see that they're not as bright and intense because the big needle is the full interaction volume, whereas the smaller needles are overlapping or mixing pixels. And so by using this deconvolution technique, we can unmix these overlapping signals. The upshot of this was that we showed that the chromium to iron ratio was about 2:1, which makes it non-magnetic, which made sense with the demagnetization of the sample. So it's really good, but this gives you a flavor for how we use data deconvolution techniques to understand and look at the chemical and or crystallographic measurements that we look at. So now let's look at the system that I really want to talk to you about. In that case here, we want to look at the cloudy zone. So on an iron, nickel, or palisite meteorite, you have the large regions of the camosite, which are forming in the case here, especially you see the typical Widmanstätten pattern. And then as the Widmanstätten pattern was forming, it was pushing all the excess nickel out into forming the plus site. And as it did this breakdown across various length scales, the boundary between the plus site and the In a camosite, you get what is called this, first of all, an ordered tetratanite rim, and followed by this smeared, smudgy line called the cloudy zone. And it's this cloudy zone that we're particularly interested in. The reason is that there was some very lovely work done by James Bryson in about 2014, where he'd shown that these small islands of tetratanite, which is an ordered iron nickel alloy of in a 1-to-1 ratio. And so these islands are, you can think of as alternating atomic planes of iron nickel, works as a very strong permanent magnet. And so it could potentially record the planetary dynamo of what's going on. However, to understand whether or not these individual islands that are on the order of 100, 150, sometimes up to 200 nanometers in size of the tetratanite are actually recording magnetic fields, we need to understand something about the nature of the matrix, which is this black structure in the cloudy zone region. It's a different material than camosite. And we had indirect evidence that suggested it was an iron 3 nickel in a FCC like lattice that you can see here. But we weren't really sure. So this is what the gist of this project was to uncover what is the actual nature of this matrix phase. But as you can see here, chemically, they're very similar, and crystallographically also very similar. So we need a technique that allows us to address these very subtle variations and pull them apart. And the reason we care about that is that using a synchrotron, and while some of you have heard me discussing, I don't really like going to a synchrotron, a lot of my colleagues, including James Bryson, Claire Nichols, and Rich Harrison, love going to synchrotrons. And they do a lot of very elaborate X-ray circular dichromism experiments in a synchrotron where they can make these magnetic maps that you see across here. And the thing that's really important is that we could find that if we cooled between about 2 degrees Kelvin per million years up to about maybe 150 degrees Kelvin every million years, we actually get really good magnetic records in the cloudy zone. If it goes much slower than the 2 degrees, the cloudy zone just gets so big, it becomes interacting and the magnetic information is not reliable. Likewise, if it cools too quickly, the magnetic information is not written correctly. Excuse me. So instead, we wanted to understand if this magnetic information, or what we think looks like magnetic information, is good information. But in order to understand that, we needed to make we needed to understand how to interpret the colors of these magnetic maps. Now that interpretation relies on you knowing what you're actually measuring. So this means that you need to have some foreknowledge about the materials, but in our case here, we don't really have good foreknowledge. So we need to re-examine the assumptions and what was going on there. And so that sets us up to the motivation for the experiments. How do we interpret these very high resolution magnetic maps if we don't know what the materials present are? And so this comes down to kind of a classic material science perspective, which is that we have a functional property, magnetism, which relies on compositional and microstructural information. Some of our earliest experiments, we jumped right away to try to attempt atom probe tomography, which we will look at the results of this. It was very informative, but it was slightly flawed in the sense that the shapes of these grains are not quite realistic. There's a lot of assumptions that go into the reconstruction, and the composition was coming in to be a bit richer in iron in the matrix than we were expecting. Likewise, we tried doing an electron diffraction technique, but this is largely 2-dimensional, and we have a complex 3-dimensional structure. So if we have these, how do we get these data sets to make sense? And the first answer here was we used a technique called 3-dimensional energy despective tomography in a scanning transmission electron microscope. This allowed us to do very accurate phase mapping chemically, and especially because there are problems with it when you try to image this with just the HAT-F signal. So to review, for those of you who are not familiar with preparing, this is a polished surface of the cloudy zone. What we would do is we would use the focus line beam to lift out and form a cylinder in a needle shape, such that we get a shape like this. And from that sharp needle, you can see that if I use in scanning in a stem in the diffraction contrast, it's all very similar because, as we said, compositionally, the two phases are very, very similar. However, if we look at it chemically, we can see good separation in iron and nickel. So now we take a tilt series, and we can reconstruct into 3D these two phases, and we can see very good separation of the two phases. And so we have from a coarse cloudy zone here, and we have a fine or a medium length. So these are about, in the coarse, the big blue tetratanite islands are in the order of 200 to 250 nanometers, whereas in the medium zone, we're talking more about 100 to 50 nanometers in size. But the thing is regardless, what we first saw is that in the coarse cloudy zone, the large tetratanite particles are actually interlaced with remnant and relic bits of matrix material. And if we looked in detail in an orthoslice through the medium cloudy zone, we can actually see that the grains of tetratanite are starting to assemble into kind of cuboidal type arrangements, very reminiscent of nickel superalloys. And this gave us a lot of hints to what kind of behaviors we should expect. However, when we first tried quantifying the 3D model that we had rebuilt here, the data was not coming out correct. It was coming out wildly inconsistent. And this is even after doing the principal component analysis on the spectra, which we used to recover these iron and nickel maps very well and to align the volumes. But then when we quantified them, the quantification was not quite right. So what we did instead, with my colleague Sean Collins, had developed a technique where we go and we moved from the unmixed signal, which we work with in the reconstructed volume, and back project to the original mixed signals from each slice, and that transforms the original signals into a series of thickness maps. In this back projection and recombination, what we're able to do is unmax how much of a contribution each pixel is contributing to each of the phases. And by assuming that we only have two unknowns, and for a total of over 30,000 pixels through the tomographic volume, you can see we have a very largely overdefined system. But by running this thickness map analysis on the tomography, based on how we segmented the data set, we were able to get a composition for the precipitates, i.e. the tetratanite particles, of 51.9% iron to 48.1% nickel, which is in line with accepted values for tetratanite. And the matrix came out to be 84.6% iron to just under 16% nickel. And at first, this seemed a little high, but then we turned our attention to our atom probe data. And here we're now looking at particles from the fine cloudy zone. So these are now tetratanites that are 50 to 30 nanometers in size. And when we looked at these grains and we looked at this analysis and using proximity data, we can see that actually our results for both the matrix and the tetratanite particles was within 1% error of what was predicted from atom probe. And this is all without using any standards, because really at the nanoscale, there aren't standards that exist that you can do. And that this is a big point of discussion that we could have at some other time. But the point being that we have two methods that ran completely independently, and we arrived at the same answer within about 1%, which was a very good result. So the upshot of this now brings us to the second complication, which is that we're still trying to interpret this. But we now have very good compositional confidence that our tomography and our atom probe, those quantifications present something where the matrix is 7% too rich in iron. So what we've done now is decided to explore the crystallography. Okay, is there something that we're not expecting in the matrix? And in this case here, we use data clustering to try and identify what are the two phases here. So the way this works is that we use a special type of diffraction technique where what we do, very similar to how you'd run a precession experiment in a synchrotron, but in an electron microscope, it's very hard for us to rock our sample through 360 degrees of rotation with respect to the beam. So instead, we can very easily rotate our beam with respect to the sample. And then we can scan the scan, and then so we rock it above the sample, and then we do a counter rock underneath of it. And what we're able to get are noise reduced diffraction patterns. And we're able to then scan that across the sample, as you saw in this little cartoon. So using that technique, we're now able to get these virtual bright field images. So if I sample a point anywhere in this data, you can get a diffraction pattern from what corresponds to that pixel location. So here we have something that looks largely like tetratenite. Here we have something that I know from experience is similar to our matrix phase. What you should notice here in these two figures is that the diffraction patterns are incredibly similar. The largest feature that's different is this bright little point out here, which for an FCC material is a forbidden reflection. And this gave us a bit of complication. And so what we did is not only did we perform a dimensional analysis or a dimensional reduction using PCA to initially first reduce the overall number of dimensions of the problem to about 5, we then threw it into a clustering algorithm. I'm going to skip there. We threw it into a clustering algorithm, and we could project then these 5 clusters into a data space described by the decomposition. And we can see that it starts to form about five groupings, depending on how you look at it. And so you're doing a clustering like that, initially looking down the 100 axis, we can identify in the tetratenite the first diffraction pattern here, where we have this symmetry, and we get this loading map, so we get this distribution of grains. We then look at the second diffraction pattern, and we finally are able to look at the third diffraction pattern. This is looking down the 100 axis. And what we're able to do then is get a good estimate for the number of grains in a particular orientation. And this confirmed one of our initial assumptions, which is that all the tetratenite orientation directions are going to be present in the sample. And that was a nice result, but it didn't tell us anything about the matrix. So we made another lamella, and this time we looked at this seemingly strange direction, the 112 tilt direction. But in that direction, the matrix, as you can see from this virtual dark field image, actually comes up very strongly. And in fact, this is actually the cluster loading map for the matrix, which again, now we have recovered this very strange, very difficult to interpret diffraction pattern, which looks at first glance like an FCC type material, but with these forbidden reflections up here. So what we did, and this is where I really like to point out that machine learning took us a long way down the right pathway in analyzing this sample. However, at the end of the day, it produced a result that was hard to interpret, and we didn't understand what was happening. So we ended up looking at the raw data again. So what we did is, because again, like I said, we have these forbidden reflections. And so what we did is we just scan back and forth across this one single point in the data. So we're not actually running a physical experiment. We're actually just looking at the raw data. In this case here, by scanning across this linear region of the matrix, watch what happens to those reflections. Okay, so let me explain again. This reflection here is a forbidden reflection. It's not expected in a cubic material. So the fact that we see it at all and we have any intensity in this point is unusual. And if we watch this movie, what we can see is that this forbidden reflection is shifting its position as we scan back and forth. So let me loop that again. So the whole thing is that these superlattice, which is due to chemical ordering in the matrix, is rotating in space. Digging back to some literature from the 60s on binary alloys, in this case, originally like platinum copper, it was shown that rotations to a superlattice like this are expected when you create what are called antiphase boundaries. So what's happening is, as the tetratenite particles grow and expand, they're trying to push all the nickel into the matrix. But because of coherency and the fact that certain tetratenite grains will maybe be at a slightly different orientation than their neighbor, the only way for the matrix to obtain and form a crystallographic structure is to create what, as you see here in this green region, areas where we end up with slightly more iron than what would be expected for the crystallographic structure that we expect. And so this is what's called an antiphase boundary, because it's a slight defect. You can see that this region up here doesn't quite align with this region down here, but it creates these. And so we expect these anti-phase boundaries on the order of every about 10 to 12 nanometers in the matrix. And so right now we were able to build a better model for how these materials grew. And it lets you set the stage for maybe thinking about how we can make other materials that are rare earth free magnets based off of these types of materials. So there's some technology implications there. And I'm going to skip over modeling, which is not the best. And so the summary here that I'd like to point out is that we demonstrate a mechanism which enables us to record why we're able to read magnetic records in the cloudy zone. We used unsupervised machine learning was very critical in identifying unique phases, even when the minerals are incredibly similar. So when you're trying to find that very weak signal against a very strong background, machine learning does allow us to start pulling those kind of details out. Crucially, we use 3D EDS tomography to protect connectivity across length scales and extend our conclusions from atom probe, all the way from the atomic up to the micron length. And finally, mapping in the electron diffraction enabled us to look for tetratanide orientations, and it gave us the actual structure of the cloudy zone. And I think with that, I'm going to say thank you very much.
Okay, thank you, Josh. Okay, actually, I'm partly persuaded by your that we don't really need to go to synchrotron to do the imaging. It looks really nice. Yeah. Actually, okay. Actually, I have I think this is worth a question that I'm thinking, because what they are doing that in particular that attracts me is that we would like to work on some, like, say, deep diamonds, or not deep diamonds, like diamond inclusions. That
yes.
Now that we think that the diamond inclusions had different sizes, and most of the previous work people published before will only look at the inclusions that were relatively big, and that me and my other colleagues that find that it's likely that most of the really deep diamond inclusions are those small particles, much smaller than what people reported, but were not recognized, analyzed by people. So if we're really looking for this deep earth phases, those were the more possible ones. But the reason that people go to synchrotron, that one reason is, say, to categorize those small particles. The other ones that people want to look at the crystal diffraction patterns, so that you identify what type of mineral it is. So in this case, I don't know that what is your, like, say, from your perspective, that what are other non-synchrotron methods that could help people in this deep diamond community to move forward with this particle analysis?
Well, so for that kind of particle analysis, you can make it comes down to a question of also, like, maybe how many particles do you need to analyze to make your conclusion, right? So, like in our case here, we have very high resolution data, but even like if you look at this atom probe here, like this atom probe result, like that, the number of grains in that particle is only like, and it's due to the size of them, within that tip, we're able to get like 120 grains of tetratanide, right? So we have a decently, 120 grains. But potentially, depending on what's the density of your inclusions in the deep diamond, if you did something like TEM analysis of that, you may not, you might get some really beautiful diffraction patterns and some nice eels. So eels would be a really great kind of chemical mapping technique for like diamonds and stuff, and especially potentially the inclusions there. But if you're only looking at a single inclusion, you have to be very careful of what kind of information am I drawing from that one inclusion. Whereas in a synchrotron, and like I said, I just personally don't like doing it. doesn't say there isn't value of going there. So going to a synchrotron, if you're trying to do lots of it and you can get lots of data, then it's definitely worth your time. And again, it depends on what's the size of the inclusions, and there might be different techniques. I can come up with all sorts of different methodologies depending on what the size of what you're trying to look at. So could it just be, do you take the diamond and you polish it very nicely and you do like a modal mineralogy? So you do EDS mapping across the entire diamond polished surface. That's one solution. But if you want to preserve maybe the full 3D structure of that deep diamond, then X-ray is kind of your best technique, and especially for synchrotron like that. So it's what is your constraint on your experiment? What can you do to how can you manipulate your sample? And then we can talk about what technique is best. I think that there's a lot of potential in maybe looking at different inclusions, but again, it depends on how many you need to look at. So what is their density? Because if there's just a couple little ones throughout an entire grain, then I could look at one. I could maybe look at two, but unless they're really close together, it's hard to map all of them.
Yeah. It is pretty difficult because for those grains that they're scattered around that, because those are the ones that people interpret as they are being trapped during the diamond growth. So it's all kinds of minerals are being trapped at the same time, not at the same time, maybe in multiple phases. And I think one reason that prevented people from doing diamond inclusion analysis as what you're doing, I think that is the difficulty of the exposure of these samples for analysis. Not only because diamond is hard, but because for deep phases, they were in equilibrium in the Earth's mantle at a high pressure. So when they brought up to the surface, they're trying to expand. But diamonds has elasticity, doesn't expand too much. So there is a quite a pressure that could be released. Actually, that's what was how the first ringwood dye that ever published before was lost after people characterized the ramen, and then when people expose the use lasers expose the diamonds, then because due to release of pressure, people heard the sound, and then those samples gone. So it's a little bit too bad. So people are looking for deep diamond minerals, and then it's very hard for people to really look at them without the exposed look at them after exposing it. So normally people look at it without exposing it. But okay, sorry, I might occupy other people's question. So if you have a question, feel free to leave a question in the chat, or you are free to open your mic to ask a question for Josh. Okay, if not, we're going to keep it our webinar for this week. And okay, thanks again, Josh, for giving the talk. It's really nice, really nice pictures, images. The 3D images are really nice. Okay, okay. Next webinar next week will be Chen Guang from UT Austin, and he's going to talk about kimberlite. Okay, great. Thanks everyone for your participation, and thanks Josh again. See you next week. Bye bye.
Thank you very much. Cheers.